Hello, we have two problems. Sorry for my absence. I was feeling really unwell, but now I'm feeling better, so I can resume recording. Sorry for that again. So the first problem we have two subspaces E1 and F1, and a subspace is said to have a codimension n if the vector space E1 has dimension n. So we have to show that this is true and this is true. And we also have E2 and F2 as the complementary subspaces for E1 and F1. So let's begin with these two statements. We can easily show it by remembering that the dimension of E is equal to the sum of dimensions of two complementary subspaces. And also the fact that the dimension of E is equal to the sum of dimensions of subspace E1 and vector space E1. So what we can do is we can write inequality right here, and the thing is we can subtract the dimension of E1 from both sides, and we get dimension of E2 is equal to the dimension of vector space of E1, and those are just the codimension of E1. Okay, this has been shown. Now, this is shown in a similar manner, so I don't want to repeat it. It's the same thing. It's analogous. So now we have this statement to prove. Now, this is gonna be quite complicated to do at start because it seems really intimidating, but it's really not that bad. So let's begin by writing down this codimension in a different form. Codimension of this is gonna be just the dimension of okay, so intersection of E1 and F1 is going to be dimension of vector space E, and then we have an intersection of E1 with the F1. Okay, now thing is we can write down that we were to add the dimension of the intersection of E1 and F1, and it's going to be resultant in the dimension of E. That's already a useful ledge to grab on. We have already connected it to a less abstract form. So what we're going to do next is we're going to add dimension of E to both sides. Again, we have this here. And I'm also going to move the intersection to another side. Now what I'm going to do is, on the right side, I'm going to write it down as the sum of a bunch of complementary subspaces. So dimension of E1, dimension of E2, dimension of F1, and dimension of F2. So dimension of E1 plus dimension of F1 minus the dimension of the intersection and plus codimension of E1 plus codimension of F1. Now, if we were to look at that, it really reminds of the fact that if we were to take two subspaces, for example Q1 and Q2, then the dimension of the sum of Q1 and Q2 plus the dimension of their intersection is going to be equal to the sum of their dimensions. Dimension of Q1 plus the dimension of Q2. Okay, and now what we're gonna do is we're simply gonna move this to the right side, And what we have here is a statement that really resembles this one. So what we're gonna do is we're gonna rewrite this in a different way. We're gonna delete this and have a dimension of E1 plus F1. What we're gonna do is we're gonna subtract dimension of E from both sides. So in the end, what we have is okay, let's rewrite this as codimension of this intersection. Codimension of intersection of E1 and F1. Okay, now we're gonna add not actually, let's subtract and next rewrite this in reverse. Dimension here, and subtraction sign. So now, thing is, E1 plus F1 is gonna be a subspace of E, which implies that dimension of E is greater than or equal to dimension of E1 plus F1, which implies that this were to substitute for variable t, for example, it implies that t is greater than or equal to 0. So what we have here is equal to this minus t, and t is said to be greater than or equal to 0, which implies an inequality. Codimension of intersection of E1 and F1 is less than or equal to codimension of E1 plus the codimension of F1. And well, dimension of E2 is the codimension of E1, dimension of 2 is codimension of F1. Okay, so we're done here. Now, the next problem. We have to show that a vector space is not the union of finitely many proper subspaces. So, let's begin by saying that this one, let's say that vector space V, actually, no, let's take vector space E, it's an easier letter to work with. We have a union like this. Now what we're gonna do is we're gonna prove it inductively. We're gonna have two cases. Actually, no, let's first write down something else. Let's say that V belongs to A. Here. Now let's say that J belongs to A. Let's say that union V not equal to J. EV. Union with EJ. Now let's introduce nice notation. Let's say that EU is equal to this. So we have here is an intersection of EU with EJ. Now let's look into two cases where EU is subspace and where EU isn't. So now, since we have two cases to check let's go ahead and do that. First case, AU is a subspace. And now thing is, we have a union of two subspaces. Again, we have said as AU and EJ, and it's gonna be a real existent subspace, one that isn't, well, broken, jagged set of a bunch of vectors that doesn't form a subspace, if and only if either EU is a subset of EJ, or EJ is a subset of EU. So what we have here is this is not gonna result in E unless either EJ is E or EU is E. Okay, but it is said that we're working with proper subspaces, so this can be true, and we have to review this case. Well, again, it's gonna be true if and only if EJ is, well, E. That is, unless we work with this scope. We still didn't review what if we're working with the EU that isn't a subspace. Okay, well, let's go ahead and check out how that would work. So this said that E equals EU union EJ. Let's say that X belongs to EU and X does not belong to EJ. Let's say that X belongs to EJ, not X, Y, and Y does not belong to EU. Now, if we fail to pick one of the variables like that, then it means that one of this is a subset of another. Well, since EJ is a proper subspace and EU isn't even a subspace, then naturally this can be true, so we can assume that we can actually pick the variables like that. So then X plus Y is supposed to belong to E. That means that it belongs either to EU or EJ, so let's review two cases. X plus Y belongs to EJ. X plus Y belongs to EU. Well, if it belongs to EU, that means that we can safely... okay, wait a second. Okay, good now. If X plus Y belongs to EU, then we can safely subtract X, and it will still belong to EU. However, we go into a contradiction. Y is supposed to be part of EJ, so definitely not this case. Let's review this one then. Well, it's a similar manner here. We can just subtract Y, and it's supposed to be still part of EJ, but it isn't part of EJ. So, by contradiction, we have proved that if EU isn't a subspace, then after union with a subspace, it's still not going to be a subspace. So the only way to retain the status of subspace in the union is for every part of the union to be subset of each other. And well, since we're working with proper subspaces, it's never gonna be E. Okay, that's it for today. Thank you for watching. Bye.